Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics. Today we will continue with model diagnostics, and that too the coverage is on autocorrelation. We have in the last lecture we have discussed something about the multi-collinearity problem, the kind of regions, the kind of detection criteria, the kind of solution criteria, then ultimately the kind of the choice of the particular models, or fixing the particular model which is actually will be the best to predict the engineering problems as per the particular requirement. But once you have the estimated model, passes through specification test, goodness of fit test, and then the kind of multi-collinearity problem, still this model may not be considered as the best until unless you check other diagnostics, and one of such diagnostic is called as autocorrelation problem. So, we have already discussed the component called as correlation, and autocorrelation is a kind of special kind of component, and mostly in the case of time series data, it very frequently occurs, and that is how to check the autocorrelation is a kind of mandatory component while dealing time series data, while doing the estimations and the kind of prediction. Even the autocorrelation also arise in the case of cross sectional setup, but it is in fact very frequent or very typical issue, or we can call as drastic issue in the context of time series data while doing the kind of prediction and forecasting. So, in these lectures we like to know what is exactly this autocorrelation, and the way we have discussed the multi-collinearity problems, we like to know what are the regions through which autocorrelation is appearing, and how to detect, and then how to solve these problems, and is there any kind of tolerance or something like that. Like in the case of multi-collinearity, if your model is actually for just prediction only or forecasting, then with multi-collinearity you can go ahead, because more number of variables will be involved, and that too it will give you high impact or high predictions. But when there is a question of reliability of the models, or the kind of quality of the kind of judgment, then that times so you cannot just go ahead like this. You have to check thoroughly and pick up the model which is good, best, and then go for the prediction and forecasting. Likewise, this is another way to search for the best fit models so far as the prediction and forecasting is concerned, to solve some of the engineering problem. So, let us see that what is exactly autocorrelation. So, it is a kind of game among the error terms. Generally, what we have already discussed till now, it is like this, that every times we have the game like dependent variables, then independent variables, for instance let us say y, x and u. Then ultimately with the process we will get the estimated dependent variable, that is called as y cap, and then we will find the error term which is the difference between y minus y hat, that is the y actual and y estimated. Okay. So, once you get the error terms, then ultimately you have actually y series, x series, y hat series and error series. So, that means after the estimation process your game plan will be y, x, y hat and then error. So, we have actually 4 different column altogether. So, now we have lots of understanding about the y series, we have lots of understanding about the x series, we have also understanding about the y hat series, and then the component called as error component, which is actually the difference between the actual dependent variables and the estimated dependent variables. So, the deviation or the kind of difference you can check from one cross sectional unit to another cross sectional unit at a particular point of time, or at a particular cross sectional unit with different points of time. So, that means there are many different ways you can actually explore the kind of issues and then detect as per your requirement. So, now once you get the error terms, that is after the estimated models you find out the difference between the actual y and the estimated y. So, once you get the estimate error term, so then there is a different kind of game altogether while we are searching for the best models which is actually very reliable as per the kind of engineering predictions or forecasting is concerned. So, ultimately you have a error component, that is E, and what will you do here? So, the error component which is actually the difference between y minus y hat, and then you have the structure called as y x and then the kind of error term. So, you may have the link between E and y, E and x. Okay. So, because this is another kind of variables, ultimately our game is how is the actually error variable environment are altogether. We will find plenty of models are there which can do the prediction and forecasting, that too with the help of only error term. So, like we have including this autocorrelation issue. So, we have actually lots of time series modeling like autoregressive modeling, moving average modeling, ARMA modeling, arch modeling, Gauss modeling. So, many advanced modelings are there where the game plans will be done with the help of error term only. So, that means once you get the estimated models and get the error term, then this time series modeling behavior will be used for the prediction and forecasting, that too with the help of error term in most of the instances. So, that is why just you guess that how is the beauty of this particular error component, because this is one of the component which can give you signal about the best beauty of the prediction and forecasting. For instance, after getting the estimated models, that is y cap, and then you will get the error error component, that is the difference between y minus y hat, and you will find if you in the simple way, if you find actually some of the error term is coming exactly equal to 0, by default the model in the most of the instances the model will be actually good for the prediction and forecasting. But if the model is not perfect one, so the line of the regression line is not the best one, then by default some of the error term will not close to 0. So, that is first instance or first indications how to justify that your model is somewhat good or something best for the prediction and forecasting. So, now what is happening? So, once you get the error term, so you will find there is there is lots of linkage with other component. So, in order to understand the autocorrelation issue, so you have to understand the concept called as lag variables. So, for instance, let us assume that there is a variables y, and the data which is having with respect to y is time specific. So, as a result we can write the variables y t, and this y t. So, we have a couple of series. Then from the y t you can create another variable called as y t minus 1, that is the actually previous on the basis of previous variables. For instance, if you start with the y 1 y 2 like this. So, y t minus 1 means it will start here only y 1 y 2 y 3 and so on. Similarly, you can start y t minus 2. So, 1 or 2 lags behind. So, this will start with the y 2 y 3 and so on. So, this is how the sequence about the lag variable. So, that will apply to the dependent variable y t. So, like y t minus 1, y t minus 2 up to y t minus k. So, n number of variables can be created. Similarly, x t, that is with respect to x. So, the original data which you can call as x t, and then we can create a new variable x t minus 1, which is the lag variable of original x t minus 2 lag variable, then x t minus 3. So, likewise you can create n number of lag variables with respect to y and x. So, now you will find there is also error terms. So, the error term can be also connected with So, for instance, let us say error term which you have already specified earlier is u t, then you can create u t minus 1, so you can create u t minus 2, u t minus 2 and so on, like y t minus 1, y t minus 2, x t minus 1, x t minus 2. So, we can have a structure called as u t minus 1, u t minus 2 and so on. So, that means ultimately what is the beauty of this understanding is that very easy to settle the kind of or create the variable. For instance, I will show you here in the Excel spreadsheet where you can actually see the data set. Okay. So, let us assume that this is a data set, and something I will give you new data set here. So, this is let us say you can create actually you just copy here some data. Let us say this is actually starts with y t and t equal to 1 up to t 31. So, that means let us say annual data, and how to create actually you can say y t minus 1. So, this is y t, and then to create a y t minus 1 just you copy again, and then you paste one lag behind. Okay. So, if you y t minus 2, then it is a 2 lag behind, y t minus 3 it is a 3 lag behind. So, likewise you can create actually n number of lag variables. Similarly, for x and also similarly for actually u. So, that means technically what is happening here, So, you can actually go to this particular component and then discuss as per the particular requirement. For instance, okay. So, that means technically we have the a kind of dependent variable y t, and then independent variable x t, and that is unexplained, then the error term u t, that is unexplained. So, now with the help of y t we can create y t minus 1, y t minus 2 and so on. Similarly, for x you can create x t minus 1, x t minus 2, which I have already highlighted in the Excel sheet how we can easily create new variables on the basis of the original information. Similarly, once you get the u t, so then you will find there may be actually u t minus 1, u t minus 2, u t minus 3 and so on. So, now what is the beauty of this particular sequence, that your current, if I say y t, so that is what actually it is like this. When I call actually y t, when we call y t, then there is y t minus 1, y t minus 1 and y t minus 2. Okay. So, this is y t minus 2. So, that means technically since y t minus 1 is derived from y t and y t minus 2 is derived from y t or y t minus 1, that by default there will be some relationship here, So, you cannot just ignore. So, that means when we will actually regress y t upon y t minus 1, y t minus 2, by default there will be a multi-collinearity problem, because all these y t minus 1, y t minus 2 are so exclusively depends upon its original data. So, that is why there is a severe multi-collinearity in this kind of situation. That means, any lag modeling you will use, so multi-collinearity is a genuine problem. So, so as a result, so autocorrelation will be also genuine problem. So, because when you are connecting y t minus 1, y t minus, for instance, y t is the dependent variable which you can predict through the help of its lag variable, let us say y t minus 1 and y t minus 2. Similarly, for x t that is the independent variable which can be also predicted with respect to x t minus 1, x t minus 2 and x t minus 2. We have actually different kind of modeling, like lag modeling can be autoregressive type, autoregressive distributive type. So, we have different schemes, and we will discuss in details in the time series modeling, but in the meantime we are discussing actually the issue of the autocorrelation, which is actually game of the error terms, and the issue of the autocorrelation, that existence of linear relationship among the error terms only. That means, technically, so when we have ut and ut minus 1. So, then we like to check what is the correlation between ut and ut minus 1. So, obviously, there will be a correlation, but that correlation coefficient should not be statistically significant. If it is statistically significant, then this will give you actually a wrong message to the reliability or the so far as the use of the estimated model is concerned to predict and to forecast the particular engineering problem. So, ultimately, so there should not be any autocorrelation problem. That means, technically if you say that what is autocorrelation and what is the extreme. So, autocorrelation means, so it is a simply serial correlation and the kind of observation about the systematic pattern in the errors. So, like there should not be any linear relationship among the regressors, that to x 1, x 2, x 3 like this. So, there should not be any relationship between ut, ut minus 1, ut minus 2 and so on, but unfortunately, so there will be some relationship between ut, ut minus 1, ut minus, because ut minus 1, ut minus 2 all are derived from the original ut. So, so when you talk about the autocorrelation, then the issue of collinearity will be coming in the picture, that with error terms. So, what is exactly this error terms? So, we will just highlight it. That means, so when you are connecting ut, ut minus 1, ut minus 2, ut minus 3 and so on. So, first of all you have to fix the lag length, what extent the you can enlarge the model. So, there is a there is a lag selection criteria which we will discuss in the later stage while dealing the time series modeling. And let us assume that the final lag choice will be up to 2. So, then technically you have the model ut, ut minus 1, ut minus 2, like this is actually ut, ut minus 1 and ut minus 2 and 3 variables. So, then you can prepare a covariance matrix ut, then ut minus 1, then ut minus 2. You can prepare a correlation matrix, and this correlation matrix you will find there will the diagonal elements will give you the variance factors, that is the error variance, and that error variance we have one assumptions under OLS, that the error variance should be uniform, or that is what it is called as homoscedasticity. That means, so all these diagonal elements. Okay, so in this 3 into 3, so we have 3 diagonals, that is the variance factor. So, these variance factors should be actually uniform, which we will discuss actually in the next lecture, that is the issue of homoscedasticity versus heteroscedasticity. But the other component, that is the off diagonals and on diagonals, which are symmetric in nature, that means ut, ut minus 1 and ut minus 2, again ut minus 1, ut minus 2, since there are 3 variables. So, we have 3 cross correlations. So, now our job is to check whether these cross correlations are 0 or non-zero. If it is 0, then there is no autocorrelation. If it is actually non-zero, then there is a autocorrelation. So, that means technically, so this particular matrix, that is with respect to error terms. So, what is the assumptions? Error terms should be normally distributed with mean 0 and unit variance. So, that means this is how the nature of the U or nature of the U must be like this. Then ultimately, so game between error terms will be here, game between error terms will be here. Then ultimately, so this will give you the signal that ultimately once you find the autocorrelation means matrix, then this will be actually transferred into a form what is the best actually. So, far as the best is concerned, let us say it is a kind of unit matrix. So, then by default all the cross correlation will be 0. So, that means ut minus 1 and ut minus 2, and then finally ut minus 1 versus ut minus 2. So, whether when there is they are consistent, then it is ut minus 1 or ut minus 1 ut. So, it is a kind of just change of the position, then ultimately this should be equal to 0. If that is the case, then there is no autocorrelation or there is no serial correlation. But if they are not 0, then by default So, it will indicate the indication is that there is a serial correlation or there is a autocorrelation. So, that means in the simple understanding the covariance between two error terms should not be equal to 0. So, that is the case of autocorrelation. If the correlation between these two error terms are coming 0, then by default so there is no autocorrelations. If the correlation covariance between ut minus 1 is actually not equal to 0, then the game will start. That is what it is called as game of serial correlation or the game of autocorrelation. And what I have already mentioned, it is very frequent and dominant kind of problems in the time series data. So, that is why it is a mandatory that you have to check the level of autocorrelations before you go use this model for the prediction and forecasting. So, that means you just see that how interesting is that just putting the input and indicating the dependent and independent and getting the estimated output, that is not the enough actually. The whole work or the beauty of the particular process will start when you will start checking or testing all these diagnostics. So, that is very interesting, and that is how the beauty of this engineering econometrics. So, ultimately what will you do actually? So, you just estimate the models, have the y bar y cap, that is then we will get the error term, which is the difference between the actual y and the predicted y, and then check what is the level of error terms, and then you check the kind of nature of correlation. So, whatever items, that is the the example is the multicollinearity, which we have discussed in the previous lecture. In real life scenario, any kind of real life engineering problem, so you will not find a situation where all independent variables are independent. So, that is how the multicollinearity problems sometimes genuine, but ultimately our requirement is how to minimize this degree of relationship among the regressors. Here also same case, since the variables are independent variables are not LI linearly independent, and some extent there is linearly dependent, and that linear dependence should not be statistically significant. After doing the processing, then ultimately you will find a situation where most of the variables are not actually highly correlated. So, that in that context these are the variables can be used for the prediction and forecasting. So, similarly in the case of serial correlation, so that means it is a step by step process. So, your first step is y with all independent variable x1, x2, x3 like this. Then in the second step, while getting the estimated model, so the first check process is the multicollinearity. Of course, we have already gone through specification test and the kind of goodness fit test. After that, you will come to the diagnostic test, that to multicollinearity issue, and you see actually whether the model can be changed or restructured somehow, re-estimate, and in such a way that the impact of this or the kind of the relationship between the independent variables should not be actually so high. So, ultimately simple message is that multicollinearity cannot be clean completely. So, in any extent it will be having always it will be there in the system, but you have to go ahead with the prediction and forecasting if your degree of multicollinearity is very low, and that too the correlation coefficient among the regressors are not statistically significant. This is also the case of serial correlation and autocorrelation. Here the relationship between ut minus 1, ut minus 2 or ut minus 1, ut minus 2, these are the kind of correlation coefficients which should not be actually not equal to 0. If the relationship between ut minus 1, ut minus 2 and ut minus 1, ut minus 2 are not equal to 0. So, that means the some amount of autocorrelation arise in the system. So, ultimately the job is now to look up to look into this problem and find out what is the degree of autocorrelation, and then think about the some kind of solution mechanism through which you can actually bring a new kind of process or estimated model, where we can actually you can do the better prediction and better forecasting without any obstacles or the kind of errors. So, that is why autocorrelation is a very interesting game, and that too very interesting again for the time series data, and that is one of the mostly the genuine problem in the time series data. So, the region of autocorrelation include the possible strong correlation between the second time with the second time t plus 1. So, usually it is happening actually in the real life scenario, and when we will be looking for the macro level kind of environment, most of the variables are interdependent. As a result, the correlation coefficient, the error among correlation among the error terms will be also having some kind of dependency. So, now we will find out what is the level of dependency and how you have to care the data. One way you can say that autocorrelation will be there when you start estimating the process with lag variable. The moment you use lag variable, autocorrelation by default will be the genuine problem. So, you must be very careful. I mean, this is the first indication how you have to start and understanding the kind of requirement. So, this is my this is one of the regression models where we have two independent variables x 2 and x 3, and y is the dependent variable, and when we estimate the model ultimately. So, that means this is the actual model, this is the actual model functional form. Then the estimated model will be y cap, that is beta 1 plus beta 2 x plus beta 2 x, and then beta 3 x x 3, this beta 2 x 2 and beta 3 x 3. So, now the difference between y t and y hat t will give you the kind of error terms u t. So, that is what here. Okay. Now, once you get the u t, you will find the u t minus 1, u t minus 2, u t minus 2, something like that, and or else you can call as u 1, u 2, u 3 and so on like this. So, that means series of error terms will be error variable will be there, and if you say that autocorrelation, the other name is called as a serial correlation, then covariance of u I u j. So, that means u 1 u 2 or u 1 u 3 not equal to 0, or the expected value of u I u j not equal to 0. If that is the case, then that is called as no autocorrelation, or there is a no autocorrelation, means there is autocorrelations. If it is exactly equal to 0, then there is no autocorrelation. So, but that means technically when you are linking error terms like u 1, u 2, u 3, u 4 like this. So, autocorrelation is a problem among the error terms, that too only of diagonals and on diagonals, not the diagonals, because the diagonal elements will be called as error variance. But the autocorrelation is a problem of error covariance. That is why every time u t minus 1, u t minus 2 and so on. Similarly, u 1 u 2, u 1 u 3 or u t u 3, where I not equal to j. But when the moment I equal to j, that means we are in a diagonal elements only, and that too at u 1 sigma square u 1, that is the error variance. Similarly, sigma square u 2, sigma square u 3. So, these are all called as error variance, and that particular detection and the kind of exploration is nothing but a new problem called as heteroscedasticity, which we will be discussing in the later part. But in the meantime, in this problems, so we like to check actually how is the relationship among these error terms. That means technically whether the covariance among the error terms are 0 or not 0. If they are 0, then the simple declaration is that there is no autocorrelation. If they are not equal to 0, then there is a autocorrelation. So, now it's more or less like multi-collinearity problem. So, if not equal to 0, then the range will be starting with 1 minus 1 or something like indefinite. So, now ultimately you have to check what is the degree of involvement in the autocorrelation, like degree of multi-collinearity. Here also you can check the degree of autocorrelation. So, there are several test statistics are there which can help you to find out the level of autocorrelation and what is that particular value where the model is actually completely free from this autocorrelation problem, and if not, what is the tolerance levels through which you can go ahead with the prediction and forecasting, or in what extent the model need actually restructuring completely. So, that means there are three different instances after the check of the autocorrelation. First instance, if there is a covariance among the error terms are coming 0 for every case, then there is no autocorrelation. So, you can go ahead with the original estimated model for the prediction and forecasting, because the indication is that there is no serial correlation. Now, if there is a serial correlation, that means the covariance between two error terms are not equal to 0. So, that means there is a problem. So, now what is how much that problem so far as the prediction and forecasting is concerned. Usually theoretically or as per the statistical rule, some minimum level may be actually not an issue, but ultimately if that particular impact is statistically significant, then definitely it will be an issue. So, ultimately, so in order to know the degree of involvement, so we have couple of statistics as I have already mentioned. So, one of the standard test statistic which you have frequently used in the case of OLS mechanism, that to estimate the models go ahead with the prediction and forecasting, that is called as a Durbin-Watson D statistics. So, it is otherwise called as DW Durbin-Watson D statistics. Two statisticians they develop this particular technique, that is simply actually Durbin-Watson D statistic, that is small d. So, which is actually covariance of error terms by variance of correlation coefficient, but that too here with the respect to error term. So, I will give you the details about the calculation of Durbin-Watson mechanism. So, if the simple understanding is that it will give you the kind of standardized value through which you can check whether there is a correlation or autocorrelation or not autocorrelation, and what extent the model will be very reliable so far as presence and absence of autocorrelation is concerned. So, it will be streamline the process like R squares and probability. So, the DW value will have some kind of standardizations through which you can actually give remarks or comments to the autocorrelation so far as the estimated model is concerned to predict a particular engineering problems or to forecast a particular engineering problem. So, ultimately, so this is how the basic understanding about the autocorrelation. It is simply the game among the error terms, and as such you need actually covariance among the error terms, and then the target is on cross correlations only, that to you have to find out covariance of y I y j where I not equal to j. So, that means only off diagonal and on diagonals components need to be checked. If there is no serial correlation, then these off diagonals and on diagonals will be coming 0, and the on diagonal elements should come to 1. So, if that is the case, that is called as homogeneity, and in that case if the correlation cross correlation of diagonals and on diagonals are not 0, then that is called as serial correlation. Of course, it is mathematically to understand is very easy, but practically we need actually a clean environment where the particular estimated model should not have any autocorrelation, but in reality to get that it is not so easy. So, that is why you have to go ahead with the prediction and forecasting with some tolerance level. So, what is the tolerance levels and how to calculate the tolerance levels, and how the model will be will not be affected with that particular tolerance, we will discuss in details in the later stage. But in the meantime, this is what the kind of game about the autocorrelation, and ultimately in order to understand the kind of nature like multi-continuity, we have no issue about the a kind of positive relationship among the regressors or negative relationship among the regressor, but ultimately we like to check whether there is a relationship or not. The case is also same here in the case of in the occasion of autocorrelation. Here since we are establishing or checking the relationship between error terms like u1 u2 u1 u3 or ut minus 1 ut minus 2 and so on. So ultimately so we are actually establishing the relationship. The moment you will get the covariance between ut minus 1 or ut minus 2 or u1 u2 u1 u3, then definitely you will find some value. Okay. So, the variance of the error term should be always positive and it should be uniform, but here these are all covariants. So, sometimes it may be negative, sometimes it may be positive, but whether it is a positive or negative, it is not an issue. Whether there is a presence or not presence, that is the major issue. If there is no presence, that means the covariance will be coming 0, and that is good sign for the modeling, regression modeling, so far as the estimation, predictions and the kind of forecasting is concerned. But what is happening in the reality? So, some kind of relationship will be there, because there is a relationship among the regressors. So, by default, so the same way the impact will come to the error term. So, there will be some way there is a relationship among the error terms. So, now we have to plot these error terms and check whether the relationship are coming positive or negative, or there is no link at all. So, that is why we have here actually no autocorrelations and then negative auto and positive auto accordingly. So, ultimately this will give you some kind of random check, and how you can go ahead. That is called as just graphical inspections about the behavior of the error terms corresponding to corresponding to the estimation of yt upon xt, that is the game between dependent variable and independent variable. So, ultimately how to obtain the error terms, which we have already discussed, but now after getting the error term, so how is the nature of this error terms, or how is the diagnostics, so far as autocorrelation, and the other counter problem is heteroscedasticity. So, we like to know all these things, how to detect all these kind of situations, and think about the kind of solution, and how you have to bring a kind of green environment where the estimated models can be used for the prediction and forecasting of any kind of engineering problem without any substantial defective. So ultimately we need a kind of situation where we have estimated models that is free from all kinds of errors, or it will in short it will pass through all the diagnostics before you use prediction and forecasting. We will discuss in details in the next lecture. With this we will stop here. Thank you very much. Have a nice day.